Hi, I'm Vincent from the Speech and Audio Processing Lab at Imperial College London. I will be presenting our paper titled Polynomial Matrix Eigenvalue Decomposition-Based Source Separation using Informed Spherical Microphone Arrays. Audio source separation is important for many applications, such as speech enhancement in hearing aids and telecommunications, 3D sound rendering, and robot audition. In real-world scenarios, however, it is often challenging to isolate the target source because of interfering sources, background ambient noise, and reverberation arising from room acoustics. The performance of these applications can be improved by using a source separation algorithm. Existing approaches to source separation includes microphone array processing, which can use spatial filtering to potentially isolate sources. There are also independent component analysis, ICA-based, and non-negative matrix factorization, NNMF-based approaches, which are successful at performing separation, but may introduce processing artifacts. In our earlier work, we proposed a polynomial EVD-based speech enhancement algorithm that operates on Eigenbeam signals for spherical arrays. The algorithm can provide good speech enhancement without introducing any artifacts. In this talk, we extend that work to source separation. The PEVD-based speech enhancement algorithm is presented here. For a spherical microphone array, we first compute the Eigenbeam signals and form the space-time covariance matrix. This is then fed into the PEVD algorithm to generate the eigenvalues and eigenvectors. The eigenbeams are then processed through the eigenvector filterbank to generate the enhanced signal in the first channel. In our earlier work, the problem is a single talker in diffuse noise. Here, we focused on multiple localized sources. Assuming that the direction of arrivals, DOAs, are provided, we can use the eigenbeams to form several modal beamformer outputs for every target. We can then apply PEVD to the beamformer outputs and recover each target signal. The proposed algorithm is summarized here. We first compute the eigenbeams using the microphone signals on the spherical array. And for every target source, we use the prior information of the source direction to generate the modal outputs, which are then used to form the space-time covariance matrix. This is then used as the input into the PEVD to generate the eigenvalues and eigenvectors. Modal outputs are then filtered through the eigenvector filter bank, and the target source is recovered in the first channel. The received signal at X subscript Q is the sum of the localized sources arriving at the Qth microphone on a spherical array. H here denotes the room impulse response from the Pth source to the Qth microphone. S denotes the Pth localized source signal. And R here is the spherical coordinate with radius R, elevation angle theta, and azimuth angle phi. Across Q sensors, we can write the data vector as the following. For a spherical array, we can represent an order-limited sound field using spherical harmonic basis functions, RLM. For the nth order and nth degree eigenbeam signal, chi of Lm, and alpha of Q here represents the quadrature weights. In the inverse transform, we can recover each microphone signal using the weighted sum of the basis functions. This diagram shows the spherical harmonic basis functions. We can, in general, formulate standard beamformer outputs using a linear combination of these basis functions, such as the hypercardioid or the maximum directivity index beamformer. Note that the 0th order term here is equivalent to an omnidirectional sensor placed in the center of the microphone array. And in this work, we also propose the modification to the hypercardioid, which excludes this 0th order term in order to avoid sound capture from undesired directions. Given the source directions, we can generate modal beamformer outputs, which can be steered eigenbeams, maximum directivity beamformer, or the proposed modified hypercardioid beamformer. Now, assuming stationarity, modal outputs are then used to compute the spacetime covariance matrix. And each element in this spacetime covariance matrix is the cross-correlation function between modal outputs ith and j. And tau here is the time shift parameter. The Z transform of the spacetime covariance matrix gives us a parahermitian polynomial matrix, R psi psi. And in this talk, we use calligraphic font for polynomial matrices and regular font for matrices. Here is an example of the model outputs on the left, as well as its spacetime covariance matrix on the right. The diagonals are computed using the autocorrelation functions, modal signals, whereas the off-diagonals are computed based on the cross-correlation function between the beamformer outputs. So this will be between psi 1 and 2, psi 1 and 3, psi 1 and 4. The PEVD of R psi psi is defined as the following, where lambda and U contains the eigenvalues and eigenvectors. The superscript P is the parahermitian operator, which includes the Hermitian transpose operation followed by a time reversal. The subspace decomposed by the PEVD generates strongly decorrelated outputs, which means that the outputs are orthogonal within the range of tau. And we denote in blue the subspace associated with the target source, and as complement as the interferer subspaces. The PEVD of the spacetime covariance matrix computed earlier is shown here, and on the left we have the eigenvalue, and on the right we have the eigenvector polynomial matrices. And to compute the PEVD, we can use any one of these algorithms. Modal signals are then filtered through the eigenvector filterbank, which produces outputs that are strongly decorrelated. Because the target source signal in different modal outputs are summed coherently, and the spectrally majorized property of the PEVD, the target source signal can be extracted from the first channel. The following target output shown on the right is produced by filtering modal outputs on the left through the eigenvector filter bank generated earlier. The following setup is used for our experiment. So we have two female speakers, and the speech signals are obtained from the timid corpus. And the two sources are spaced 90 degrees apart. The acoustic environment we first consider is anechoic. We compared our algorithm with two modal beamformer outputs, namely maximum directivity index and the modified hypercardioid beamformers, as well as state-of-the-art approaches, the auxiliary IVA, aroma, and fast MNMF, which are based on the ICA and non-negative matrix factorization approaches. We evaluate the performance of the algorithm using source separation metrics, such as the SDR, SR, SAR, which are the signal to distortion, interference, and artifacts ratio respectively, as well as speech intelligibility and quality measures, STOI and PESC, to quantify any potential speech artifacts. For this example, the proposed PEVD outperforms in delta SDR, SAR, STOI, and PESC, whereas the fast MNMF approach leads all algorithms in delta SIR. Across all metrics, the larger improvement offered by MH cut over maximum directivity index also highlights the advantage of excluding the 0th order eigenbeam in the model beamformer. Let us now listen to the signals. Here is the received signal.
The hallway opens into a huge chamber. Why, Nora, the very idea. Those who teach values first abolish cheating.
By eating yogurt, you may.
The maximum directivity index beamformer.
The hallway opens into a huge chamber. Why, Nora, the very idea. Those who teach values first abolish cheating.
By eating yogurt, you may.
The modified hypercardioid.
The hallway opens into a huge chamber. Why, Nora, the very idea. Those who teach values first abolish cheating.
By eating yogurt, you may.
Right, let's hear the received again.
The hallway opens into a huge chamber. Why, Nora, the very idea. Those who teach values first abolish cheating.
By eating yogurt, you may.
The PEVD.
The hallway opens into a huge chamber. Why, Nora, the very idea. Those who teach values first abolish cheating.
By eating yogurt, you may.
Observe that PEVD does not introduce processing artifacts, and the non-target speech signals are attenuated, but they remain intelligible. Let's compare it with the fast MNMF.
The hallway opens into a huge chamber. Why, Nora, the very idea. Those who teach values first abolish cheating.
I now present source separation results for a reverberant room with a T60 of 0.7 seconds. The SDR score on the left shows that PEVD in blue is comparable to ICA-based methods shown in pink, red, and orange, and is in fact the best in STOI score. So in the paper, we also note that the positions of scenario 1 for 2 female speakers, they are different from the configuration for scenario 2, which involves 2 male speakers. And the details are in the paper. In this talk, a polynomial EVD-based source separation approach that uses informed spherical arrays have been proposed. The proposed approach is among the best performing algorithms for source separation, but does not always outperform them. The approach performs separation without introducing any audible artifacts, whereas other algorithms considerably distort the signal as part of performing the separation. These are the references used in this talk. Thank you for listening to this talk. If you have any questions, feel free to email me. And for listening examples, please visit the following URL, or you can scan the QR code.